Hello, everyone. We are going to start the second day of the workshop. We have many interesting talks, and you will see. And the first of them will be given by Adrián del Río. Adrián studied the PhD here in Valencia with our group, and he has done a postdoc in the Instituto Superior Técnico of Lisboa. And next year, he will start a project in the Pennsylvania State University with Professor Astekar. Nowadays, we are collaborating also with Pepe Navarro in a study of the quantum effects in the gravitational collapse. And today he will talk about gravitational wave signatures of black holes area quantization. Adrián, when you want.
Okay, thank you, Pau. And thank you, the organizer, for giving me the opportunity to talk here in this workshop. So here in this talk, I will essentially describe the implications that black hole area quantization may have on gravitational wave physics from a purely phenomenological point of view. And well, this work done in collaboration with all these people listed here, and based on this paper in the archive. Okay, so let's see if I can change the slide. All right. So, given the future observable expectations in gravitational wave astronomy, it seems natural to ask whether gravitational wave physics, or to study whether gravitational wave physics can have the potential to extract information about quantum aspects of black holes, and not only to test the validity of classical GR in the strong field regime. So, although we still don't have a fully established theory of quantum gravity, there are still some insights that could be inferred based on general arguments. One of these is the fact that black holes in the quantum theory are expected to have a discrete energy spectrum. That this is the case is a direct consequence of black hole area quantization. This is a property of black holes that, well, a feature of quantum black holes that was first pointed out by Bekenstein in the 70s, based on general arguments, heuristic arguments. But then it was later realized in different theories of quantum gravity that indeed black hole area quantization can be manifested well, because of several details, right? And well, we will assume here in this work as a starting point the Bekenstein area quantization for all I'm going to say. The point is that if quantum black holes, so if black holes in the quantum theory have a discrete energy spectrum, this means the lessons from quantum mechanics is that the frequencies of gravitational waves that these black holes could absorb in principle should be discrete as well, should be quantized. The question that we're posing here in this work is whether these characteristic absorption frequencies of a black hole, whether these are observable or not, whether they can have an impact on gravitational physics or not, right? In order to have an idea of how this goes, to provide an order of magnitude estimate, let me give you the following simple situation. Suppose you have a Schwarzschild black hole, okay, with mass m, and you have an incident wave, gravitational wave of frequency omega, that interacts with the black hole. Classically, this wave will be absorbed and you will get another black hole. Suppose, for simplicity, that this black hole were excited to another Schwarzschild black hole. Because in the quantum theory, the ABM mass of the black hole is discretized, this means that the values of the frequency of this incident gravitational wave should only take a discrete set of values given by the values provided in this slide. Now, the funny thing here is that if you evaluate the coefficient of these frequencies, so the value of this, the typical order of magnitude of this frequency, what you find is that the frequency signal of the gravitational wave lies within the LIGO-Perico band. In principle, observable, right? So this simple example illustrates that black hole area quantization may have the potential to leave observable imprints in gravitational wave physics. Now, the thing is that, unfortunately, this calculation was actually too naive. I was cheating a little bit because I was completely ignoring black hole rotation at all levels. And the ingredient of black hole rotation is fundamental, at least for two reasons. So it's important to take black hole rotation into account in order to analyze these things because it could be tricky. Okay, so First of all, the energy spectrum of a black hole not only consists of Schwarzschild black hole state, but it also includes all the spinning states that would correspond to classical configurations of a Kerr black hole in classical GR. And the result of joining all these states together into a single spectrum is a highly regular distribution of points, a highly non-uniformly spaced spectrum. This means that joint spectral lines might be much closer than previously considered in the above example, and in particular, the frequency of absorption could be much smaller, meaning that, well, they could be out of observable reach, okay? So this is important to take into account. On the other hand, black hole energy states in the spectrum should be unstable because of Hawking radiation. This means, if we extrapolate lessons from atomic physics, that these energy states of the energy spectrum should have an effective linewidth. And it could be the case that astrophysical black holes may recover an effectively continuous absorption spectrum by taking this into account due to overlapping. In atomic physics, typically this linewidth increases with rotation, and it could be the case that astrophysical black holes, which do have a non-negligible rotation, makes a difference with respect to what I've just mentioned. So our goal in this paper and in this talk will be to discuss all these issues in detail and to figure out whether black hole area quantization still has the potential to provide, well, some gravitational wave phenomenology of black hole area quantization. Okay. So as I mentioned, the Bekenstein energy spectrum is rich and highly non-uniform, but for the particular problem of gravitational absorption, can a black hole be really excited to any higher energy state in the spectrum? In other words, are all the energy states of the spectrum accessible for the absorption of a particular gravitational wave mode? Relative transitions of a black hole induced by the interaction of a gravitational wave could be studied with a Hamiltonian of this form, in which the main piece describes the Hamiltonian of an unperturbed black hole, and in which we add a small perturbation describing the interaction of this black hole with the gravitational waves. Okay. So we are not attempting, as I said in the beginning, we're just approaching the problem phenomenologically. We're not attempting here to provide a mathematical accurate description of the problem, but we are interested instead of finding some results from general arguments. So, for instance, if we assume that the black hole in the quantum theory behaves as an ordinary quantum mechanical system, we can think of its Hamiltonian as having a complete set of orthonormal eigenstates with some eigenvalues given by the classical ADM mass that would be discretized according to Bekenstein. This eigenstate would describe the classical configurations of black holes in GR, okay, described by mass and black hole spin, but discretized. Not all possible classical configurations would be allowed in the quantum theory. Now, we would be interested here in considering transitions, studying transitions between different eigenstates of this quantum black hole induced by the absorption of some gravitational wave. Then, if we apply familiar results from time-dependent perturbation theory in quantum mechanics, this means that the absorption probability distribution will be picked around final values of the ADM mass, which differ from the original ADM mass by the energy of one quantum of this incident gravitational wave, as usual. So, well, besides this energy conservation, the important thing here to notice in this slide is that angular momentum conservation will impose another constraint, a selection rule in the language of atomic physics, right? So if we focus our attention, for instance, to quadrupolar gravitational wave modes, which are the dominant modes in most processes in astrophysics, generated in astrophysics, this angular momentum conservation means that the black hole will be unable to absorb the incident gravitational wave mode, quadrupolar mode, unless the corresponding frequency intersects or matches one of these characteristic absorption frequencies of the Bekenstein mode, which is compatible with angular momentum conservation, okay? So despite the initial complexity of the Bekenstein spectrum, the only accessible energy stage for the black hole to be excited to is actually a small subset of the whole spectrum. So this solves the first question that I posed in the motivation. On the other hand, we know that black hole energy states pseudo-spontaneously decay according to Hawking radiation. And this translates into an effective line width on the energy state. The energy states are not simply lines, but they have some thickness, right? The calculation of this line width can be estimated using semi-classical arguments in following standard arguments in QFT encoded spacetime in quantum field theory encoded spacetime, right? As for instance, space theory in the 70s, we can just follow his treatment to calculate what we're interested in order to get these line widths. And the results of the calculation can be essentially summarized in the figure. Okay, in this figure, we plot these characteristic absorption frequencies of the Bekenstein model as a function of black hole spin A. Okay, for each value of n, for each value of area number transition. Okay, the dependency with mass is trivial; it's just 1/m, so we just multiply with it so that we remain with only a function with one variable. And so we can essentially see the whole thing on this figure, right? On top of it, we superimpose the line width obtained from the Hawking radiation. Okay, you can see here that these lines have a certain line width. Okay, so there are two important messages that conclusions that one could extract from this figure. First of all, we find that there is no overlap of the spectral lines, except if you go to extreme high rotation. For this particular case of alpha equal to 4 log 2, this means that you need to go to higher values of 0.9 in the black hole spin in order to recover the overlapping. The second message is that there is a minimum absorption frequency for the quadrupolar gravitational-wave mode to be absorbed. Okay, for the black hole to be excited to another higher energy state. So this acts as a threshold, similarly to the threshold that appears in the photoelectric effect. So in some sense, this is analogous to the photoelectric effect. So from these two last slides, what we find is that we conclude that there is room enough for finding phenomenology of black hole area quantization in gravitational waves. So we found, in particular, two concrete ways of testing the hypothesis of black hole area quantization, at least following Bekenstein's, using binary black hole observations. One regards the ring-bound states of this binary, and the other one regards the spiral phase. So let's discuss first the ring-bound states. The ring-bound signal after the collision of two black holes is known to be very well described by black hole perturbation theory, and in particular by the quasi-normal models of the final black hole remnant. After the collision, gravitational waves are produced and described by these quasi-normal models, and although a great part of the energy, essentially the majority of the energy, goes to infinity to our detectors in the form of gravitational waves, still a significant fraction of these waves will be directed towards the horizon, where, according to classical general relativity, will be completely absorbed. Now, according to this logic, if we take into account Bekenstein area quantization, this is no longer true. Absorption will only take place if and only if the real part of the quasi-normal mode frequency, which is given in this figure by the red line, intersects one of the characteristic absorption frequencies of the quantum black hole, which is one of these black lines. And what we find is precisely that this intersection, this matching between this resonance between the two frequencies, only takes place for a specific subset of values of the black hole spin. Otherwise, the black holes will disperse these waves and propagate again to infinity, producing in this sense an echo of the original signal. So the detection of these gravitational wave echoes could be used to infer the value of alpha, the fundamental quantum of black hole area in the Bekenstein hypothesis. In turn, this could be useful to discriminate between different area operator proposals in quantum gravity. For instance, in quantum gravity, there are different proposals. There's a canonical proposal for the area operator, but there are others that would provide a value of alpha. Okay. So the second test that we found, the second way of testing the black hole area hypothesis, quantization hypothesis, is associated with the spiral phase of the binary black hole. So classically, we know that these two components of a binary, these two black holes will absorb part of the gravitational waves generated during this orbital motion. These waves produce tidal forces that distort the horizon, and it is known since the 70s that when a black hole rotates under some distortion, the rotational energy is dissipated. And in the context of the binary, this energy will be transferred to the evolution of the binary, to the orbital motion. So this means that the absorption, so that the two components of a binary system are black holes, well, that the two components of a binary system absorb gravitational waves means that they contribute, so this phenomenon contributes to the evolution, to the determinism of the binary. Now, as I said, we find a threshold in the black hole absorption spectrum, and because the gravitational waves that are generated during spiral have such a low frequency, it is highly expected that this wave will be highly suppressed. And so we expect a different binary evolution with respect to the prediction of classical general activity. And this could be studied phenomenologically by introducing some parameter in the gravitational wave phase signal, well, to model this non-absorption or absorption depending on the value of the black hole speed. So this was done in the context of exotic compact edges, and we are just here extrapolating some results. The conclusion is that future advanced detectors could be will have the potential to discriminate to probe this parameter gamma here. Okay. And well, to conclude, let me just summarize what I've just said. We argue that gravitational astronomy has the potential to extract information about quantum aspects of black holes, namely of the potential to test the hypothesis of black hole area quantization. In particular, we found two ways of testing this: through gravitational wave, through the production of gravitational wave echoes, and through testing the binary evolution during a spiral, consequence of the suppression of tidal heat, the phenomenon of tidal heat that I've just mentioned in the previous slide. We argue that these two mechanisms could provide two different ways of testing, of measuring the fundamental quantum of black hole area, this parameter alpha that appears in Bekenstein hypothesis. And lastly, I would like to mention that, as I have emphasized several times during the talk, this relies on a phenomenological approach, but a more accurate description would require a more deeper understanding of the fundamental black hole degrees of freedom, and especially the interaction of these black hole degrees of freedom with at least a classical gravitational wave. Still, well, we hope that this work could encourage work on this direction, and well, in general, we expect this phenomenology to offer a way to start experimentally testing quantum theories of gravity with gravitational waves. And well, this is everything. Thank you so much for your attention.
Thank you, Adrián, for this interesting talk. Now, let's see if someone has any question.
Do you have any estimate of the amplitude of that this quantum effects could have in the spectrum of the radiation, of the gravitational wave? Sorry, could you repeat that a bit louder?
Yes. Do you have any idea or an estimate of how important these quantum effects could be compared to the classical amplitude of the gravitational wave?
No, we don't. Well, that would depend on the amplitude of the gravitational wave echo. And no, we don't really. That would depend on the so that would depend on the details of the absorption probability distribution that we don't have information about, right? So the amount of gravitational echoes that could be produced, I mean, here we assume a trivial probability distribution. Let me go back to the previous slide. So let me focus on this slide, right? The red line describes the real part of this quasi mode frequency, one could assume a trivial probability distribution, meaning that when the intersection takes place, the absorption is 1, the probability distribution is 1, and when the intersection doesn't take place, as for instance here, so I'm not sure if you can see my pointer, but when the black and the red lines do not intersect, you could expect that the probability of absorption is 0, right? So if that is the case, then the 100% of the initial amplitude will be dispersed. So the gravitational-wave echoes should be relevant. The point is that in practice, this is a trivial probability distribution. In practice, you will have certain, if you work this out from the perspective from, say, from first principles, from a quantum theory of gravity, you would get a distribution, a non-trivial distribution. So you wouldn't get such a trivial statement of saying, okay, when there is no intersection, the probability of absorption is 0, so you would completely disperse the whole amplitude, and so on. I don't know if I'm explaining myself. Do you understand what I'm saying?
Yeah.
So in principle, this toy model would tell you that the whole gravitational wave would be dispersed, would produce an echo, if the real part of the quasi-normal mode doesn't intersect one of the characteristic absorption frequencies. But we expect not the 100%, but maybe, I don't know, 70% or so, roughly, in practice. But for getting a quantitative prediction of this, we would need a quantum theory of gravity. So that would depend, in fact, from the prediction of, so this could be used to test experimentally quantum theories of gravity. If you have a theory of gravity that tells you that this is the amount of gravitational wave echoes that you should expect in a LIGO event, and you don't find that, that would mean that something is wrong in your theory, right? But from the point of view, but for here we can only give you a qualitative statement. We cannot give you numbers.
Okay,
right?
Any idea of the importance of this, for instance, in a supermassive black hole or in a very low mass black hole? So for microscopic black holes would be easier to observe these quantum effects?
For microscopic black holes, the thing is that if you know with interferometers, so let me go back to the previous slide, first slide. So here, as you can see, it depends on the characteristic absorption frequencies depend on the mass of the black hole. For typical astrophysical black holes, and for this I mean intermediate intermediate solar mass black holes, say 50, 100 solar mass black holes, the frequencies lie within the LIGO-BRIGO band. For microscopic black holes, the frequency would be super huge, and you wouldn't be able to observe them.
Okay. There are questions.
Yes, there are two questions. The first one, what do you mean by gravitational wave echo?
Right. So gravitational wave echo, I mean, so, okay, that's a good question. So when you have a binary black hole, right? When the two black holes collide, the final remnant of the black hole is, say, vibrating, and this emits gravitational waves. Now, these waves are classically these waves are directed towards infinity and towards the horizon. The waves emitted towards infinity are the waves that one could expect to measure from the typical LIGO-BRIGO event, right? But the waves that go towards the horizon, according to GR, will be totally absorbed, right? The thing is that if you have other thing than a black hole, either an exotic, something that is called an exotic compact object, or here what we call quantum black hole, the interaction of this gravitational wave with the surface of an exotic compact object or with this quantum horizon will make not 100% of these waves to be completely absorbed, but a fraction of them will be dispersed. And this dispersion of waves would give you a second burst of gravitational waves after the arrival of the initial burst that was propagated to infinity initially, right? I hope with this I can answer the question.
Mm-hmm. Okay, and another question from Jose Navarro. Is there any special kinematical configuration for the in-spiral to enhance the effect?
Well, not particularly. I mean, it depends on the kinematical configuration would determine the dominance of one gravitational wave mode over the others. Typically, the dominant one is always the quadrupolar mode. If you change, so if you add some, say, precession or things like this, you will excite, classically, of course, gravitational waves of other modes. And well, that would mean that you have to do the whole analysis for these modes. They will have a different absorption spectrum, and you could expect, say, different phenomenology, in the sense that for each gravitational wave mode, you would expect echoes for a given black hole spin or not. And well, this could enrich the phenomenology. But with regard of the gravitational wave echo, I don't think so. I don't think that is important at all. So that will only depends on the, say, interaction of a black hole with the gravitational wave. The kinematic, so the inspiral phase is just to produce these waves, not for the. It doesn't really. It's not really related to the interaction of the, say, on the amplitude that a gravitational wave echo could have.
Mm-hmm. Okay, so I think there are no more questions. So thank you very much, Adrián.
Thank you.